The main difference that is between ASM and flowcharts that is going to be shown in almost everywhere that you would try to read is that in ASM charts there is a consideration of time. So there is timing consideration when we talk about ASM chart. But it is difficult to understand how this timing consideration is taken, and if it is taken, how it is any different than how we would determine and analyze time when we are talking about conventional flowchart. Now it is kind of interesting because this book is really good, by the way. I would recommend it and suggest it in the comment box, in the description box below. So if you can see here in figure, there is an ASM chart for design example, and you can see how this whole process is taking place. First, there is initial state, and then it goes to the state S. This is the state box. Okay, if you don't want to call it state box, you can call it decision box, because depending on the decision of this state box, there is either one more relational box or conditional box that is going to follow, or it is going to reset the state to initial state. So there is this decision box, which if it is set to 1, then your whole process starts or it remains at the initial state. If S is equal to 1, then there are two flip-flops A and F which are set to 0. Now this is an example of an up counter. At the end of this whole flowchart and ASM chart, you would observe that we want to increment our number. So if you are not really familiar with up counters, then I would just say that up counting is counting from smaller number to bigger number. So assume that you are counting from 0 to 8 here, okay, or 0 to, if you're mostly it is based on the number of bits you have. If you have 4 bits, then 4 bits are equal to 15 in decimal. So if you have 4 bits, you count from 0 to 15. If you have more than that, you count more. If you have less than that, you count less. But here in this diagram specifically, there is counting from 0 to 8. Now, so for counting, we have to increment. So if S is set to 1, then everything is going to be reset, because in initial state might have been the third state or fourth state or even the eighth state. We don't know. So we are going to reset it. So by resetting, we are resetting register A or flip-flop that constitute A, and flip-flop F to 0. Okay, A, F, and E are the 3 flip-flops or 3 registers that are going to be discussed in this ASM chart. So A and F is set to 0. Then there is incrementing of A. Okay, then after incrementing a 3 bit is checked. Now A is your number and its bits are A4, A3, A2 and A1, where A4 is the MSB or most significant bit. Now, assuming that we are starting from 0, what you would do is first increment A by 1, so that goes to 1. Then when you have 0, 0, 0, 1, A4, A3 and A2 are equal to 0. Only A1 is equal to 1. Okay, so A3 is equal to 0, E is set to 0, and we go back to the state T1. A is again incremented, and you get now 2. Still A3 is equal to 0, as only A2 bit has been assigned 1, because the binary value for 2 is 0010. So only A2 bit is set to 1. Then again, A is set to 0 and go back to A. Then it is incremented to 4. Now, after 3, of course, still 3 does not change A3. So I'm skipping to state 4. When you have finally reached state 4, A3 is actually changed. A3 is changed from 0 to 1, right? Because the binary equivalent of 4 is 0100. So you have 1 at the place of A3. Okay, then after some time, if A3 is equal to 1, E is set to 1, and A4, based on the value of A4, either you come back to this initial state or you go to this state. But as we know, A4 is still 0, so we go back to this state and increment 1. Now from 4 to 7, there would be of course no change in bit 4, A4. A4 is set to 1 when we get 8, right? So when A3 is equal to 1, not really 8 as well, because in 8 you have to follow this part, right? When A3 is equal to 0 and then A4 is equal to 1, then it would be equal to 8, but that would be the initial state. Okay, if you got confused here, just think that if A3 is equal to 1, then we go to A4, then if A4 is equal to 1, then we go to the initial state. So for if A4 is till now not equal to 1, so this state is going to continue. When A4 is equal to 1, we go on to the next state of T2, and then initial state is achieved. Because when F is set to 1, we go back to initial state. This is how we have defined this whole logic function. Now, so these, as you can see, there are general words or general symbols that have been assigned to specific states. This is state T0, this is state T1, and this is state T2. All of these states are really unique, they symbols actually, and they represent an ASM block. Okay, ASM block is something that has one state box and one to many conditional boxes or even decision boxes. So what it actually means is it is just one block, okay, which is going to work together. Now this whole block, as you can see, is working together. This is so distinct, you can actually tell just by looking at the ASM chart, not even trying to analyze the chart, that this whole circuit is going to be together and it is going to work on achieving T1 state again and again and again. How? If A3 is equal to 0, E equal to 0, and we achieve T1. If A3 equal to 1, A4 equal to 0, we achieve state T1. So this whole body is trying to go back to the state it was initially present. So you have assigned it a symbol, that is T1, to differentiate it from the rest of the circuit, because it is not like the rest of the circuit. This is a different circuit because it is talking about initial state and going back to the initial state again. Okay, going back to the initial state again. That's why this circuit is also a different circuit, because it is constituent of achieving the initial state again and again. So that's why this ASM block associated with state T0 is unique to this chart. Again, when you have set A4 to 1, then F flip-flop is set to 1. Now this is so distinct, it is not really related to this block or even this block, honestly. It is related to this blocks after F is set to 1. Then it goes to the this ASM block, and it goes back to T0 state. But up to this portion, it is a really unique category, and it follows after A4 is set to 1. It is not going along with the assignment of A3 or going along with T1 state. It is different because it is only dependent on the output 1 of flip-flop A4. If not flip-flop, it would be the bit A4. Okay, so this is a different block. So this was all explaining what are ASM blocks, what is typical ASM chart, and how it is different from flowchart. We'll start now. But when you're talking about flowchart here, it is important that you know that flowchart is going to be almost similar to this. Might be the case that there would be different symbols sometimes. That is not really the case actually. The only plus thing that is a little bit different here in the depiction, I am saying, main thing is the timing thing, but in the depiction you would see that oval shape here, this actually determines your conditional box. Conditional box is something that is present at the output of the decision box. So these are the decision boxes, and at the output of these or exit paths of these decision boxes, you have conditional boxes. Conditional boxes because they are stimulated when the conditions are met, and those conditions are when the decision box gives the true value. Now, it might really not be true. If you see this, you would say it's not true. But it's true for this function, na? True is when the function gets active. So this box is getting active when A3 is equal to 0. If it's not active when A3 is equal to 1. If A3 is equal to 1, then this box is active, right? So by true, I mean the part where it gets stimulated, or it actually uh, e- gets some value to start off with. So maybe saying true is not really the correct thing here. I would say the condition, when it meets the condition to satisfy its execution. Okay, so when the outputs of the decision boxes satisfy the conditions that are required for the execution of the conditional boxes, you have the value being set. So here E is set to 0 if A3 is equal to 0. Okay, so this was about conditional boxes as well. But our main motto is to understand the difference between flowchart and ASM chart. Now, when we are talking about flowchart, what you would think basically when you're looking at this diagram is, after initial state has been achieved, you go to state S. After S is set to 1, you go to state A, state T1, and before that you're setting A and F to 0. After going to state A T1, you're incrementing A to A plus 1. Then you are checking the value of A3, and then you are setting something E equal to 0 or equal to 1 based on the value of A3, and then you go back to the state T1 if it is set to 0, or the other way around. Now you assume everything to be going on simultaneously in case of flowchart. After this step is there. After this step, then this, then this, then this, then again this, and so on. So that is the main difference between a flowchart and an ASM chart. So if you have analyzed this, if you have understood this flowchart, it is, please understand this because I am going to change the frame now. So now we are going to talk about ASM. Now here, this is the chart that we are going to make, or I would say state table, that, or a sequence of operations that are being followed by that particular chart, okay, or that particular diagram that we just saw. Now every block in ASM chart specifies operations that are to be performed during one common clock pulse. This is also one definition of ASM block. ASM block is not just where you have one state box and maybe multiple conditional and decision boxes. There is one more thing that specifies it, that is the clock pulse. When you're talking about one ASM blocks, the whole thing that is carried out there, you have to think of it as being carried out during one clock pulse. That's what is going to differentiate it with the rest of the flowcharts that we have seen. Okay, how? Let's observe. So as we can see in this table, you have first 0, then 1, then 2, then 3, a typical up count as you can see. Okay, then as you go to 0 to 1, from 0 to 1, okay, why is E and F 1 and 0? It is explained here that E is assumed to be 1. Okay, in this line, the value of E is assumed to be 1 because E is equal to 1 when T0 at T0, and because E does not change during the transition from T0 to T1. We are starting off from this state now. We are analyzing it and creating that diagram. Now when you are going from this state to this state, what is the value of all of this E, F and A registers or flip-flops here? Let's analyze. Now E, what is E? It is equal to 1. How? Because we have got 1 here, and then you have got A4 1 here, then F is set to 1, then you go to this state. Alright, so E here is equal to 1. Okay, because from this path to this path there is no change of E. F is equal to 1 and A is something based on whatever it is, maybe 100, 010, whatever. Okay, so I'm not talking about initial A. Initial A here, because if A4 is equal to 1, it might be 100. Okay, let's take 100. So F is equal to 1, E is equal to 1, A is equal to 100. When S is set to 1, you would clear A and F. So F is now cleared, so you have A equal to 0, F is equal to 0, and E is not cleared, so E is still equal to 1. So we are talking about this state here. at T1 state. Now when we are transitioning from T0 to T1, there is a change in A and F, but there is no change in E. So we can assume E to be 1 here. F is equal to 0 here. So this block is actually determining all of the bits as well as the flip-flops as well as the A3 and A4 and the state. Okay, the state that is being there. So we are talking about T1 state now. So E and F here, as we just saw, are 1 and 0. Okay, E was initially 1 and F was actually reset, so it became 0. Now when we go to the next state, as we know, E is still going to be 0 throughout till we reach A3 equal to 1. Okay, till we make A3 equal to 1, E is not going to change, right? Because A3 is equal to 0 makes E equal to 0. If A3 equal to 1, then only you get E equal to 1. So that's why this chart says that till we reach the part here, till we reach this part, in the first block, in the first four things, you can see that E is equal to 0 after this, after this, after this, because it does not change till A3 is equal to 1. Now, one doubt you would have when you observe the next block is, why isn't E becoming 1 when A3 is equal to 1, right? Because if A3 equal to 1, then E should be equal to 1, but it's not happening here. Why? That is the main difference between ASM and flowchart. ASM does not consider that everything is going on after one step after one step. It considers it to be going on according to a pulse. Okay, now see the relationship between time at which A3 becomes 1, right? A3 becomes 1 and time at which E becomes 1 is 1 clock pulse later. Why? When does A3 become 1? When you think about it, A3 would become 1 when you add 1 to 0, 1, 1, right? When you add 1 to 0, 1, 1, you will get A3. So, at this state, when you have 0, 1, 1, you are adding 1 and you are getting A3. But here, the present state of A3 is taken into account, right? So you are adding 1 to 0, 1, 1, fine. But now, at this particular moment of time, you don't have A4 equal to 1. You don't have okay, we are actually not 0, 1, 1, sorry, 0, 0, 1, 1, okay? So adding 1 to 0, 0, 1, 1 will give you 0, 1, 0, 0. So adding 1 to this is going to increment the state A and give you 1, 0, 0. But 0, 1, 1 is the present state, and in this present state you have A3 equal to 0. So you are going to talk about the present state. As in the present state A3 is equal to 0, your E is going to be 0. E is going to set to 0. You have incremented A and then you got 1, 0, 0, fine. Then in the next pulse it would determine it, and then you would have E equal to 1. Okay, to understand it better, see, when A equal to 0, 0, 1, 1, the next clock pulse increments the counter to 0, 1, 0, 0. But the same clock pulse sees the value of A3 as 0. Okay, right? When you had 0, 0, 1, 1, the clock pulse did increment it to 0, 1, 0, 0. But right now in that block, A has not actually changed. It will increment after this, right? It will increment after this whole process is done, then it will come back and increment. At this particular time, you have A3 equal to 0. So at this particular clock pulse, as A3 is equal to 0, E is going to be cleared. E is equal to 0. It is not going to be set. When you have the next clock pulse, now think about it. You incremented A from 0, 1, 1 to 1, 0, 0, okay, or 0, 1, 0, 0. So now you have 0, 1, 0, 0. Now you can see that A3 is equal to 1. Now in the same clock pulse it is equal to 1. Okay, so now you can not increment, assign 1 value to E, because in this particular present clock pulse, you can see that A3 is equal to 1. Okay, so now after one clock pulse, you are going to set E to 1, F is still 0. Okay, so now as we go in the next clock pulse from 0100 to 0101, okay, now A3 is initially equal to 1. We see the initial state. Okay. So initially when we are changing from 0100 to 0101, as you can see, the third bit here is 1 and we are determining the value of A3. Now A3 as it is equal to 1, E would be set to 1. Okay. Similarly, if by the same logic, try to analyze what would happen here. In this particular section, after when trying to imagine it again, you have A3 1 for this whole cycle, right? And then A3 became 0 again at A4 equal to 1 in this cycle. Now, will E change that from as, will E change quickly as our A bit or A register changes from 0, 1, 1, 1 to 1, 0, 0, 0? Will it change after this? A3 is equal to 0 here. So when we are thinking about in the sense of a flowchart, you would think that, okay, now our E bit should be equal to 0 as A3 is equal to 0. But as we just said, it is going to see initially what is your value of A3 and A4, right? Initially, when we are changing from 0, 1, 1, 1 to 1, 0, 0, 0, 0, the value of A3 is equal to 1. That's why E is not going to immediately change to 0 just because in the next clock pulse you would have A3 equal to 0. So in the initial state you have A3 equal to 1. So you would have E equal to 1 here as well. Okay, in the initial state you have A3 equal to 1. Now when you increment 1, 0, 0, 0, 0 to by 1, initially the value of A3 as you can see in 1, 0, 0, 0 is equal to 0. That's why it is going to reset or make or clear actually E. Okay, E is going to get cleared because initially the value of A3 is equal to 0. In the next pulse, as 1001 is there, E is set. Okay. Now F is going to be 0 throughout because we are yet not gone to that phase where A4 is 1, E3 is 1, both are 1 1. Then only we are going to talk about F equal to being 1. Till now that has not happened because either A3 was 1 or A4 was 1. Okay. Now if A3 and A4 are both equal to 1, now again in these four pulses what was happening? Now E has been reset. Again, when A3 becomes 1 again, would you change E directly to 1? No. Why? Because it is going to get changed in the next pulse. Okay, in the next pulse. From 1100 to 1101 is the part where E is going to be set. Why? Because when you are changing from 1011 to 1100, it is going to check the initial state of A3, which is equal to 0. That's why E is equal to 0. We know that if A3 is equal to 0, E would be 0. And if A3 equal to 1, E would be 1. Okay, following that logic, as initially A3 was 0, E is 0. In this case, when you incremented it, initially A3 is equal to 1. So in the next state, you got E equal to 1. Okay. So now you have reached the place where 1101 is the state and E is equal to 1. F is still 0 because we are not considering that part. Okay. Both A3 and A4 are equal to 1 now. E is set to 1. This block is now done. Okay, we were actually differentiated every block. This is going to be simultaneous, but when I mean T2 and this last part of T1 is going to be simultaneous. Sorry, T2 and T0 is going to be simultaneous. I apologize. T2 and T0 is going to be simultaneous because just after we achieve T2, we go back to T0. So So at this state, when both A3 and A4 are equal to 0, we can see it is shown in the next pulse. It would happen just after it, by the way. You can show it in one pulse, but to show the change in E first and then change in F first, this is a better way. So you have F becomes 1 because now A3 and A4 both are equal to 1 initially. Okay, so you have F is equal to 1 as well, and you have state T0. All of these states are, as we know, when both are 1 1, you have state T2, then you go back to state T0, and so on. Okay, now as you can see from the operations, it might seem as if all of the operations are delayed by 1 bit. That is the main difference between a conventional flowchart and an ASM chart. In flowchart, you would assume that we are going to talk about the present state, that in the present state itself, there would be a change observed in E bit. Okay, so we would think that if A3 is equal to 100 and it is changed, A3 is equal to 1 actually. I meant the register A is equal to 100. So that means that A3 is 1. Now if A3 is 1, in flowchart you would assume that E would be set to 1. That's it. We won't think about whether it is initial state or whether it is next state. So the time is taken to be simultaneously. I mean, just after you're looking at A3, you look at E, then just after looking at A4, you look at F, and everything is going to be done simultaneously without consideration of clock pulse. That is the main difference. So if we were drawing this state diagram or operation sequence table for the flowchart, there won't be this gap. E would directly become 1. Here as well, E would directly become 0. Here as well, E would directly become 1. There won't be one more clock pulse delay to define that. Okay, so flowchart is that's why different comparatively. So thus the value of A3 is to be considered in decision box from value of counter in present state before there is any increment, as E belongs to the same block. We are talking about the same block when we are saying that this block, or this block. As E belongs to the same block as A3, A3 did not. Why is it saying same block? If by any chance you were talking about this block, if E was present here, then the incremented portion is going to affect E, right? If this, because A3 is going to give some output and then A is going to be incremented, and that is going to go to this part. For example, I'm assuming it is there and it is connected like this, okay, assume that there is one arrow pointing here. So if A3 is changing from 0 to 1, okay, now and E is present here, because you're incrementing it and it is changing from 0 to 1, the next state, as it is connected to the next block and next state, it is going to be changed till at that particular point only. So you don't, so for it, in the next state for it is 1. So just as you are saying from 0 to 1, you would have in the same block, you can write that F, or if E was here, that E has been changed, right? But as we are talking about this sequence, E is changing after A3 is changing, right? So not even changing, E is not changing, sorry that I was wrong there, E is not changing after A3 is changing. It is changing one pulse before, right? So if A3 became 0 to 1, it became 0 to 1 after E is assigned the value. A3 was 0, it was assigned 0, then it became 1, fine. But that will affect the next E. It won't affect it now. Okay? That's the main difference that has to be considered. So first there would be generation of signals in the present state, as you can see, and then in the next state there would be execution of those signals. We generated signal and we would execute it in the next part. Okay, The operation in hardware are mostly in blocks, okay, and they by blocks I mean the ASM block. This operation is going to be along with this block, this operation along this, and this operation along this. So the hardware operations in these blocks occur during the same clock pulse. That is the main definition of ASM block, that all of the operations are going to be held in the same clock pulse. So they are not going to be in sequence of operations. Okay, what I mean by this is after the process of A is done, then we would look at E. After the process of E is done, then we would look at increment. That is not how an ASM chart is going to work. It is going to work in the same pulse. Thinking about working on A first, then on E next is how a flow chart works. So it works on the sequence of A, then E, then again increment in this diagram as we can see. Okay, so it is important now to analyze what we said until now. So in a conventional flow chart, we would assume that A is first incremented and the incremented value would have been used to check the status of A3. And then we would check the status of A3 and apply the value to E. Whether E would be set or cleared would be based on the status of A3. So we would assume A is first incremented. That's the main difference. But in ASM chart, A is not incremented first. A is incremented after E is set or E is reset. E is going to be set with some value and then there is incrementing. As you can see, then there would be some increment. Okay, so that is the main difference. So for a conventional flow chart, you won't see the delay if you are going to draw the state table or diagram. Okay, I wish it was clear. It mainly focused on timing sequence, this whole conversation, because that is the main thing that distinguishes it from a conventional flowchart. If there are any doubts, please address it.